All right, so we're going to pick up where we left off. So I like to do this at the beginning of every lecture, is kind of summarize a little bit where we've been. So the moral of the story so far is, step one is we want to figure out what's the frequency content of different signals. Okay, so that's our desire. For a reason that I haven't really made clear yet, but I promise you that it will become useful to take signals and split them up into frequencies. So then we said, okay, well, the only signal that is a pure frequency, like that contains exactly one frequency and nothing else, is a cosine. That's just like the definition of a cosine. It's a pure tone. It only contains one frequency by definition. So therefore, if our goal is to take a signal and break it into a bunch of frequencies, therefore our goal is to take a signal and break it into a bunch of cosines. Okay, that's what we're trying to do. If you want to understand the frequency content of a signal, you have no choice but to break it into cosines. Then we said cosines are well and good, but they're kind of a pain to work with for a couple of reasons. One is they don't really integrate very cleanly, especially when you multiply them against other functions. So we said, how about this? Instead of working with cosines, we're going to work with complex exponentials, which are basically the same thing, right? Not basically, they're actually exactly the same thing if you put them together right. And I promise you that there would be all sorts of savings in terms of effort. Okay? And then finally, in class, we came up with this formula where we said it's called the inner. Really? Did I lose a marker over the weekend? Inner product integral. Okay, and the inner product integral basically answers the question, how much e to the j omega t is in x of t? Gentlemen, I can't talk over you, please. Okay, a equals 1 over t, integral over 1 period, x of t, e to the negative j omega t, dt. Okay? And that's where we are. So, and we tested it. That was the last thing that we did on Friday, right? We tested it with a kind of a dumb case, right? I gave you a cosine, and then we tested to see how much cosine there was in that cosine, and we got exactly what we expected. And if you read in the book, you should have seen that I tried a different frequency, and it was 0, which makes sense, right? What was my test signal that we used? Was it cosine 3t? 3 cosine t, right? So if you say x of t is 3 cosine t, right? If I ask the question, how much omega equals 1 is in the signal, right? You'd better get 3/2, right? Because we know this is equal to 3/2 e to the jt plus 3/2 e to the negative jt. So if you run the inner product integral and you say, hey, how much e to the j omega equals 1 t is in that cosine? That's what we did on Friday, right? We ran the integral, and guess what we got? We got 3/2. Okay? Which wasn't terribly surprising because we could have just solved that by inspection. Now in the book, I try another example. I'm going to spare you the calculus because I think everyone can read. But if I come along now and I try another frequency, like if I come along and say, how much omega equals 2 is in that cosine? Okay? Well, if this is a pure tone, that means it only contains one frequency, omega equals 1. If it only contains one frequency, how much should it contain of every other frequency? It should contain 0, right? So we know, again, by inspection that our answer should be 0 because this is a cosine. It only contains one frequency, that frequency. Every other frequency, it doesn't have any of it. Okay? Well, it turns out in the book, we do the integral, and when we do 3 cosine t e to the negative j 2t and do that integral, we get, in fact, what we expect a equals 0. And if you try any other frequency, you get 0, as expected. So, what I wanted to do today was to say, okay, this is all well and good because we could have just guess this answer, right? This answer was just kind of obvious. So what we're going to do today is we're going to try some other signals, okay? And we're just going to work through the problem from beginning to end and see if it makes any difference, okay? See if we can actually see about building a signal out of cosines, all right? So let's start by taking a vote on what signal we're going to do, all right? I don't really care. In the book, I do a square wave, and in recitation, you're doing a square wave. And I guess we could do a square wave in class, but if you want to do a sawtooth or a triangle wave or a, whatever wave, I don't know, any votes? Sawtooth. Okay, we'll integrate by parts. That's fine. All right. Okay, let's have what's the period of my sawtooth going to be? Pick a number. 2 pi? Good God. Okay. 2 pi. No. We're going to stick with it now. 2 pi? All right. Let's see. What's the easiest way to do this? 2 pi. Can we all agree that's a periodic sawtooth? Okay. And it goes back on in infinity. All right. So here's x of t. That's awful. X of t. Here's t. And you want the period to be 2 pi? Okay, fine. Okay, so if the period is 2 pi, this is 0. What number is this? That better be pi, right? If you've decided you want the period to be 2 pi, then that number better be pi. This number better be minus pi. Okay, so minus pi, 0, pi, okay, 2 pi, 3 pi, and so on. We good? You picked a good one. We're going to, you're going to get your money's worth out of your tuition dollars today. Okay, before I go any further, I need an equation for this line. X of t equals. I'm going to give you a hint. It's a line. Oh, I guess should we do minus 1 to 1? Right. Rise over run, man. That's great. Good. What's my rise over run?
1 over pi.
1 over pi. So that's my slope. Right. So it's 1 over pi. So is my answer t over pi?
Yep.
That's the equation of this line?
Yeah.
Okay, good. And I know that's right, because if I stick in t equals pi, I get 1. And if I stick in t equals negative pi, I get negative 1. So we're good. All right. Now, I'm going to tell you this the same way I told everybody last semester. There's going to be several occasions where you have to find the equation of a line, as I've drawn it on a picture. Okay? This cannot be the part of the problem that gives you fits. In fact, I think last semester, I'll have to go back through my notes and check, but people kept screwing this up so much. Like I would draw a line, and we'd have to get the equation of the line as not even the first step of the problem. That was like step 0 of the problem. They still couldn't do it. And I'm like, you're never going to get these integrals if you can't even get the equation of the stupid line that you're integrating. We actually wound up having a quiz where I gave them a line, like I drew a picture of a line, and I said, find the equation of the line, right? A quiz for points. And I told them it was coming, and not everybody got a 5 out of 5. So that was awesome. But you guys are better than that, right? You look like classy, well-educated people. Okay, so let's go ahead and set up our integral. So my period is 2 pi seconds, which means the frequency is 1 over 2 pi hertz, which means my frequency in rads per second is 1 rad per second. Well, that's nice. I like that. Okay. So we are going to test. Can I build this signal out of just one cosine? No, obviously not. It's not a cosine. So I'm going to have to use a bunch of cosines. Yes.
Question. So you're saying that the frequency is 1. So isn't that a pure tone then? If it's just 1.
No, that's a good question. So the question was, if this is the frequency, doesn't that mean it's a pure tone? And it doesn't. That's a good question. If it was a cosine with that frequency, it would be a pure tone. This is some other signal that's periodic, and it still has a period, it still has a frequency, and but it's just not a cosine that's periodic. It's some other signal that's periodic.
Is it because it's not continuous?
It's continuous.
Well, the continuity isn't
No.
sharp spikes.
No, even if it didn't have sharps, that wouldn't be a problem. What you're going to find is, if it was a pure tone, if it was a cosine, then this would be the only frequency that I need to rebuild it. But because it's not a pure tone, not only am I going to need omega equals 1, but I'm also going to need some other frequencies.
So technically, you have energy at other frequencies than 1.
Absolutely. I have energy at other frequencies than 1. But right now, we're just going to start with 1. We definitely need this frequency. We definitely need omega equals 1. But we're also going to need some other frequencies. Okay, let's just try it and see how it works out. So we're going to start by answering the question, how much omega equals 1 is in this sawtooth? You ready? Here's what we're going to do. We're just going to write the integral, right? It's just plug and chug at this point. So it's 1 over t. So what's my t? It is 2 pi. Integral from... Now, here's where you got to put your thinking cap on. It's totally legit. You've only got to integrate it over one period. That's what the rule says. Now, if you wanted to, you could integrate it from 0 to 2 pi. But if you integrated it from 2 pi, look at the mess you would make for yourself. If you integrated it from 0 to 2 pi, I would have to use this formula, t over pi, from 0 to pi. And then I would have to use another formula for x between pi and 2 pi. So that's 2 formulas for x, right? Because this formula, t over pi, that only applies over here, but it doesn't apply over here as well. So that would mean I would have to do 2 equations, 2 integrals. Now instead of integrating from 0 to 2 pi, what if I integrated from minus pi to pi? Can I use the same equation for x of t? Yes. Okay, so that's it. I make it a little easier for myself. I don't have to do it that way, but I like things that are easier. Okay? So I vote that we integrate it from minus pi to pi, and it's going to be x of t. So x of t in this case is t over pi, and then it's e to the negative j omega t. So e to the negative j, or omega in this case is 1, exactly the same frequency as my signal. So j 1 t dt. And now you got to integrate. Well, that's a mess. What do you want to do about that? Hey, the pi comes out. That's pretty nice. Table. That's totally legit. Did you hear what he said? A table of integrals. If we didn't have a table, how could we integrate this? By parts. Okay. And even integrating it by parts wouldn't be that pleasant. But I'll totally take integration by table. So why don't you tell me what the back of your book says, and then I'll write it here, and we'll make it fit our equation.
It doesn't have it, actually.
It doesn't have it? Baloney. All right, let's see. T e to the a t. So I learned this trick for integration by parts. I'm going to break this up like this. Anybody learn this trick? Yeah. So on the left side, I'm going to take the derivative. On the right side, I'm going to integrate. So 1 over a e to the a t, 0, 1 over a squared e to the a t. So in other words, the integral of t e to the a t is going to equal t over a e to the a t minus 1 over a squared e to the a t. There you go. There's your table. Yeah.
Just because I always forget to have how you assign the plus minus. So that's what screws me up.
Yeah. So first of all, has everybody seen this tabular? This is basically just a shortcut for integration by parts. So this is the thing that I'm trying to integrate. I break it into 2 pieces. The piece on the left, every step I take the derivative. And on the piece on the right, every step I integrate. Okay, so t, derivative is 1, derivative 1 is 0. On the right-hand side, e to the at, derivative, integral is 1 over a, e to the at. Integrate again, you get that. The final step is, you do it till you get to 0. So then you multiply, and so then it's plus, so it's this expression minus this expression. And if there were more steps, it would be plus, minus, plus, minus, plus, minus.
So it always starts plus, minus, plus.
Right, and then it ends when you get to 0. Okay, so let's see if we can use this table of integrals to solve this problem. Okay, I think we can. So I'm going to pull out this pi. So 1 over 2 pi times 1 over pi. Now, what is my little a? Yeah, if I want to match this up, the little a in my table of integrals is whatever's stuck next to the t, which is negative j, right? So let's see what we've got. We've got 1 over a, e to the at. Okay, if this is a, what's 1 over a? Everybody remember how to play this game?
Negative.
Yep. Absolutely. Remember how to play that? If a is negative j, then 1 over a is 1 over negative j, which is just ugly. So you multiply by j over j. That gives you j over, j times j is negative 1, times the negative is positive 1, so that's j. And while we're at it, we're also going to need 1 over a squared. What's 1 over a squared going to be? Negative 1, because it's going to be this expression squared. And j squared is negative 1. Okay, so let's see if we can do this. So we've got t e to the minus jt minus 1 over a squared. So it's minus negative 1, so plus e to the minus jt, and we're done. Well, that's pretty easy, right? I'm just applying integration by parts. Have I made a mistake?
So we need tj, or j to the t,
Oh,
e to
yeah.
the negative, so we have 1 over a.
Oh, snap. Yeah, the 1 over, I forgot the 1 over a, so there is a j here. Absolutely. Right, that j is the 1 over a. Thank you. Good. That would have ended badly, and I wouldn't have found it. We okay?
Limits of integration.
Yeah, we still need the limits of integration minus pi to pi. Okay. And just because I'm lazy, does anybody care if I factor out the e to the minus jt from both terms? That'll just make it a little less stuff when we actually get to the substitution step. So that's going to be e to the minus jt times jt plus 1 minus pi to pi. tj, jt, who cares, right? Same difference. I hope this works. I wish I hadn't erased that. That's going to be a handy integral to keep around. Should probably write it down somewhere. Okay. Should we sub in? We're just subbing in for t now. So equals 1 over 2 pi times 1 over pi times big old square brackets e to the minus j pi. Right, so now I'm substituting in pi for t times j pi plus 1 minus e to the positive j pi minus j pi plus 1. That's not so bad, especially when you consider what's about to happen.
Yeah, that's in the negative j pi, and then j pi positive
sort of, but you got to think about, we got to deal with the e to the j pi first. So what is e to the j pi? All right, here's e to the j 0. Here's e to the j pi over 2. Here's e to the j pi. So if this is 1 and this is j, what's this? Negative 1, right? You guys remember that? Real, imaginary. Here's e to the j 0. Here's e to the j pi over 2. Here's e to the j pi. So if that's positive 1 and that's j, this number best be negative 1. Okay, so this number is equal to negative 1. What's e to the negative j pi? Same thing, right? If I go e to the minus pi over 2, e to the minus pi, guess what? I'm in the same spot. So this is also equal to negative 1. So let's simplify this mess a little bit. 1 over 2 pi, 1 over pi, times, okay, so it's negative j pi minus 1. Now we've got to be careful here. 1, so negative 1 times negative 1 is plus 1. Plus 1 times negative j pi is negative j pi. And then plus 1 times plus 1 is plus 1. The 1's cancel. I'm stoked about that. So in the brackets, I'm left with negative 2j pi. Oh, that's fun. Look at this. 2 pi cancels that 2 pi. And I'm left with negative j over pi. Wow, all sorts of stuff disappeared. Okay, almost done. This is the right answer. It's not wrong, but we're not quite finished yet. I want to express, remember, my goal is to express a in a complex form. Not as a cosine. Well, this is a. This is the coefficient. Okay, in a minute we'll peel apart what this means. But always I want to express numbers in polar form. Is this in polar form? Is it a complex number? Yes, we should be able to express it in polar form. Remember, all polar numbers need to be magnitude e to the j phase. Okay? So, hook me up. Magnitude's 1 over pi. I think we can all agree on that. 1 over pi. I will not argue with that. Now we need to know where we're talking about. Right. Okay, so if this is my complex number map, where am I? Am I down here?
Yes.
Right, because there's no real part. Right, so I don't have to go left and right. So it's just imaginary, but it's negative imaginary, so it's got to be down there on that axis. Okay, how far down is it on that axis? It's 1 over pi units down. That's what the magnitude tells me. Right? What's my phase angle? Well, I could either go the long way around, which is nothing wrong with that, or I can go like that. I like that way better. Minus pi over 2. And we're done. All of that was for one frequency. Okay, let's pick apart what that even means, okay? Let's pick apart what that even means. So, I asked the question, how much omega equals 1 is in x of t, where x of t is our sawtooth? And the answer is A equals 1 over pi e to the negative j pi over 2. All right? So I want to focus first. So let's write this as a cosine. Okay, let's actually write the expression for the cosine. All right. So if A is that, what's my best fit cosine for this sawtooth?
K is 1 over pi
Right, remember it was k cos omega t plus phi equaled k over 2 e to the j phi e to the j omega t plus k over 2 e to the minus j phi e to the minus j omega t. See how fast I can do that? You should be able to do it that fast. I've done this about 400 times. That's how you get better at it. If you want to know how you can get better at it, you have to do it 400 times. Okay. So, if that's my identity, I'd like to be able to write this cosine as, like this. So what's my k? Right? I take my magnitude, double it, and that should give me k. So if that's my magnitude, if I double it, I should get 2 over pi cosine omega is 1 t, and my phase is minus pi over 2. All right. So before we plot this in MATLAB, we have to ask the very important question of, does this make any sense? So how about it? Does it make sense? Oh, snap. No, 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 no. Okay, good. Sorry, call the projector. All right. So let's start with the amplitude. 2 over pi is about 2/3. Do we want a 2/3, like, is a cosine of amplitude 2/3 look like at least in the right ballpark?
One shifted to the right by pi over 2.
Hold off on the shift for a second. I'm just talking about the amplitude. I mean, is the height about correct?
No.
It's about 2/3. It's not awful. I mean, it's not off by a ton, right? I mean, it's not. It didn't come out to be 10,
0.6.
and it didn't come out to be like 0.1. I mean, it's in there. Like, it's within a factor of a very little bit. So I think the height is roughly correct. But right, what you were saying, I want to focus on the phase shift. Why did the phase shift come out to be minus pi over 2? What does a cosine look like with a phase shift of minus pi over 2? It kind of looks like a sine, right? If this is a cosine, and you shift it, give it a phase shift of minus pi over 2, that shifts it to the right by pi over 2. Okay, well, what does it look like if you shift it to the right by pi over 2? You're not going to believe this. You get a sine. Now, look at this picture. Does that look appropriate for this? Absolutely, right? If we had a cosine, if we fit this with a cosine that was peaking up there, we'd have a mess on our hands, right? But instead, what the math told us was that the best fit cosine is going to look roughly like that. See how it nailed the phase angle for us? Any other phase angle would just leave us with a mess. So here's what we're going to do. We're going to go back and forth a few times. We're going to build this thing piecemeal. And hopefully we're going to do like a few harmonics at a time. Can you see? You cannot see. Send a projector. Laptop. It's plugged in, dude. Oh, it's doing something on my end. Okay. Don't worry. I'm not even going to bother pulling down the screen because we're only going to do this for a couple seconds. So let's see. T equals, I don't know, ln space minus, I don't know, minus 10 to 10. X equals, don't worry too much about this. Rats. What's the is there sawtooth? Oh, there is a function called sawtooth. 2 pi times my, it's just sawtooth of t plot tx. Let me just see if this works. Okay, does that look roughly like the signal we are trying to recreate? Grid. Okay, does it have a period of pi, or 2 pi?
No.
Who said that? Sure it does.
No.
Sorry, I didn't mean to bust your chops. Throw him out. There you go. Does that have a period of 2 pi?
Yeah.
Sure it does, right? Here comes the downwards wiggle. Okay, so it's the wrong phase shift, but it's got the right period, right? Here's 0, here's 2 pi, goes from -1 to 1. So I just got to give it a little bit of phase shift and I'll be good to go. So let's see, if I want to give it the right phase shift, let's see, minus pi over 2. No. Oh, no. I want to shift it by minus pi. There we go. Okay, now does that look better? Hint, yes it does. Okay, here's a sawtooth. Here's minus pi. At 0, the y value is 0. And then at pi, it goes all the way up to 1. So this is, in fact, the same sawtooth that I have drawn on the board. Okay? So far, I've just made the sawtooth. Okay? Now, let's plot on top of it the cosine that we just derived. Are we in agreement? Okay, so here's what we're going to do. So let's see. C equals, I got to look over my shoulder, 2 over pi times cosine of t minus pi over 2. T minus pi over 2. Hold on. Plot t, here let's call it this, C1, because there's going to be other C's in a minute. Okay. Let me put the screen down so we can... I'm sorry?
What's hold on?
Oh, what does hold on do? If I don't do hold on, then the new plot would obliterate the old plot. Right? If I said, first I did plot, I got the blue signal. If I then said plot for the red signal, the blue signal would disappear and the red signal would be plotted. But if I want them plotted on top of each other, I issue the hold on command, and then it'll just keep plotting them on top of each other. Yes?
Are those spaces, this is kind of a weird question, are those spaces between the sawtooth and the cosine, are they, if you combine those two spaces, kind of, would they add at the space at the top?
You mean this space?
Yeah, that space and the one parallels the,
Like this
would those two add to that space?
Would these two? I don't know. That's a good question.
I mean, there's kind of relationship there? Or?
I don't think there is. But gosh, what I don't know, I mean, there might be, but I don't think so. That might just be coincidental if they look like they're similar. Okay, so we have the right, okay, so the red signal is in fact the one that we just calculated by hand. So it looks like it's okay. It's not awful. It's not great. But at the very least, I'm pretty psyched that we got the phase shift correct, right? The integral correctly predicted a phase shift of negative pi over 2, and that totally worked. Okay, so it's a start. Any other questions or observations about this?
It's only between the lines. It's not, the corners are not.
Right. It does a pretty good, the red signal does a pretty good job of sort of catching the overall shape, or like the frequency of the blue signal, but it does an awful job of catching the corners. Okay, yes, and that's not an accident.
Is the red signal called the fundamental?
Yeah, you can think of it as the fundamental frequency, and I'll get more into that in a second. Okay, now I'm going to do something that's going to drive you bananas. Trying to figure out how to turn off the screen here. How do I... Oh, seriously, that worked? You know, they don't train you how to use this stuff, right? And they don't like, the day you get your degree, they don't say, hey, I'm going to teach you the secret pass. Oh, see? It came back.
It's a bit flaky. It does EJ RGB conversions.
There we go. What if I just unplug that? Oh. Don't make me turn you off, projector. That's it. Okay. Okay, so we figured out how much there was of omega equals 1 in the signal. But that clearly wasn't enough, right? I mean, when we plotted those two signals against each other, clearly we have a lot of work to do to rebuild our sawtooth out of cosines. So we need another frequency. Okay, we need to add more cosines into our signal. So here's the magic-y part. Okay, the part where you're going to have to take it on faith. We tried omega equals 1. Okay, we got an answer. Now we're going to try another frequency, and we're not just going to pick one out of a hat. We are going to stick to, so as Eric was saying, omega equals 1 is called the fundamental frequency. Because it was the same frequency. It was the same frequency as the sawtooth. Now we're going to stick to integer multiples of the fundamental frequency. Trust me. I'll come back and revisit the why in a second. Those are harmonics. Okay. There's a rule that says that whenever you're in a situation where you have a periodic signal, it only contains energy at integer multiples of the fundamental frequency. And they're called harmonics. Any periodic signal is built out of harmonics of the base frequency. So, for example, right now, we've just completed testing omega equals 1. What's the next frequency that we're going to investigate for our sawtooth? 2. We're only going to do integer multiples of this number. Turns out this number is 1, so integer multiples of it are just going to be 2, 3, 4, 5, and so on. We are going to have to go to infinity, which is a bit of a drag. Oh, that's a great question. We're doing the negatives already. Because look what happened. Because remember, we just did omega equals 1, but guess what we got for free? Negative 1. That's why we do complex numbers, right? I did one integral. Look at this. I did one integral, and look what I got you. I got you k, and I got you phi. Okay? So we got, and that was because we did the positive and the negative frequency at the same time. That's why we use complex conjugates. Okay? If we did this in the cosine domain, we could totally do that. Okay? We just have two integrals, and it would be awful. So yeah, we're doing the negative numbers like kind of for free. So here's what I'm going to do. Without erasing anything on the board, I'm going to get you your answer for omega equals 2. Right? So we've answered the question how much omega equals 1 in x of t. Now we're going to try omega equals 2. So watch this. That was easy. Okay. Now I've got to, let's see. So now my a is equal to 2j. So 1 over a is, right, it's half j. And this is going to be negative 1 over 4. Okay. So let's work our integral. So now there's a 2 here that wasn't there before. And a 4 here that wasn't there before. Is that right? See, I knew you were going to hate me because I can do this with a whiteboard marker, like super easy. And you basically can't do this in your notes. But you're smart folks, for the most part. I don't, just kidding. Okay, so let's see here. So we still pull out the e to the negative jt. Yeah, why don't we pull out a quarter as well? If I pull out a quarter, then I need to stick a 2 in here. Does that work? Okay. Limits of integration still the same? Yeah. Okay. So, yes?
Do we need the 2 in the exponent for that second step?
Yeah, totally. There's a 2 here as well. Yeah, absolutely. Yeah, we can't skimp on that. Okay. So let's see here. We still got our 1 over 2 pi. We've got our 1 over pi. I'm going to pull out a quarter I'm going to pull out this quarter. That leaves me with, so I've got e to the minus j2 t, where t is pi. So it's e to the minus, so that I just put a 2 up there, right? Okay. So now it's 2j pi plus 1 minus 2 and 2. Is that it? Holy smokes. Okay. All right, so cleaning this up a little bit. Okay, I think I'm just going to erase now. Okay, so I've got 1 over 4, 1 over 2 pi, 1 over pi. Okay, e to the minus j 2 pi. Right, here's e to the 0, minus pi, minus 3/4 pi, minus 2 pi. So this number is equal to 1. So 1 times 2j pi plus 1 is just 2j pi plus 1. So 2j pi plus 1. E to the 2j pi? 1. So it's minus is plus 2j pi. And then it's minus plus minus 1. Okay, so once again, my 1's cancel. And in the parentheses, I'm left with a 4j pi. So let's see. So my final answer is, let's see, the 4's cancel, the pi cancels. I'm left with I'm left with j over 2 pi. Is that in polar form? So if I want to write that in polar form, I get what? Magnitude, 1 over 2 pi, e to the j, positive pi over 2. Easy, right? Okay, let's go add that cosine in. So now we've said, erasers over here. In a minute, we'll automate this whole process, because I don't want to, you know how I said I've got an infinity of those integrals to do? You think I want to do these in like this integral an infinite number of times? Heck no, right? That's for suckers. So in a minute we're going to automate the process so that we don't have to keep doing this. But for now it's just I'm trying to make a point. Okay, so now we said how much omega equals 2 is in x of t. And the answer is a equals 2 over pi e to the j pi over 2. And if we were to write that as a cosine, we would get 1 over pi. Is that right? No. 4 over pi. Wait, what? Oh, sorry, I had 1 over 2 pi. I'm just trying to rewrite that number over there. Sorry, there we go. That's what I just solved. So what's my cosine going to be? It's going to be 1 over pi. Cosine of the frequency I just tested, which is 2t, plus pi over 2. Before it was minus pi over 2, now it's plus. Okay, so let's do this. Let's go ahead and let's plot it again. And then I'm going to send you home with a little homework. Not like homework to hand in, but homework to actually just, use your brains for a bit. Come on. Okay. Now while it's brightening, I'll type. So we just did C1. Now we're going to do C2, which is going to be 1 over pi times cosine of 2t, 2 times t, plus pi over 2. Is that good? Okay. So let's have C2. Well, let's plot it in another color. How about, yeah, good luck seeing green on the screen. How about we do magenta? Everybody likes magenta. Okay. So let's look at what we've done. So this is the new harmonic that we've just figured out. Okay. So first of all, you can see a bunch of stuff makes sense. It has double the frequency of the first harmonic. That's good. It's got the opposite phase, but at least it still lines up at 0. Okay, so that's kind of good. So now what am I going to do with the red signal and the purple signal? I got to add them. That's the name of the game. I know that my sawtooth contains this red signal and it contains this blue signal. So what I really need to do is actually just to add them together. So instead of plotting them individually, well, sorry, in addition to plotting them individually, I'm going to add them. C1 plus C2, and I'm going to plot them with a big black line. Now, what do you think? Isn't that neat? Okay, look at what just happened, right? Look at what just happened. I added the red and the purple signal together, and all of a sudden, I get something that's asymmetrical, in the exact same way that my sawtooth is asymmetrical. And furthermore, now we can start to see the wisdom, like some of you were complaining that my red signal only had an amplitude of 2 over pi. It wasn't big enough. But why didn't we want to make it bigger? Turns out that we needed to leave it a little bit smaller because we still got to add on to it some of this other cosine, right? If we made it any bigger, it would have gotten too big. I mean, look at this. Now the black signal is sort of approaching the right height. I mean, that's okay.
Couldn't you make it bigger and subtract?
You can, but we're not subtracting. The whole point is to keep adding cosines together. We're adding and adding and adding. We're just adding more ingredients to the recipe. You can't you can't take things out.
I guess it does intuitively make sense because the definition of an integral, with calculus is an area and a curve. But we're just building it out of cosines now.
That's right.
Finding the area, just summing them all up.
That's right.
Into that area.
Yeah.
If omega equals 2 is 0, would it still be called a harmonic?
Is 0 a harmonic, you're saying?
0 is a multiple. If there's no omega 2 in
Oh, if it was just 0, would you still call it a harmonic? That's a great question. So for some harmonics, like if we were doing the square wave, for example, we would have solved the omega equals 2 case and gotten 0. Okay, it turns out when you make a square wave, you don't need any of the second harmonic. It's just kind of a weird thing. You still call it the second harmonic. It's just that you don't need any of it. Yes?
For this particular example, do you need every harmonic?
You need every one, I think. Yeah. Okay, so here's your parting thought for today. Here's what I want you to think about. And this is where we'll pick up. Oh, I'm not going to be here on Wednesday. John is going to come give you your lecture on Wednesday. I am being sent somewhere that I don't want to go to, but I'm going. I mean, I had a choice, but, it was one of those things where it was like, hey, you. No, it's professional. It's not child care related. Anyway, here's what I want you to do. So can we all agree that doing this integral infinity more times will be time consuming? Okay, we can all agree on that. So here's what we're going to do. 1 over 2 pi, integral minus pi to pi. T over pi, none of that changes. The only thing that's going to change, if we did the third harmonic, I would change this 2 to a 3. And the fourth harmonic? 4. Okay, how about this, smarty pantses? What if, instead of a 2 here, I put an n for the nth harmonic? Okay, and then we would call this a sub n. How much do we need of the nth harmonic? I submit to you that you can do everything that we've just done here, and you'll get an answer that you'll get a number, and there'll be an n in it somewhere. Okay? And then, if I say, what's a sub 6, instead of having to do the integral, you'll just come here to the answer and sub in 6. All right? What do you think? In fact, I'm willing to guess you could just eyeball the answer based on what we have so far. I mean, it ain't rocket science, right? I mean, for omega equals 1, it was 2 over pi cosine t minus pi over 2. What do you think the third harmonic is going to give us? It's going to be 2 over n pi, right? Because here n equals 1, here n equals 2,
Cosine of NT.
cosine of nt.
And the shifts, they're going positive, negative.
Right, the shifts are going to go back and forth. That I can just tell by eyeballing. But still, I want you to do this. So at home, this won't take long, I don't think. See if you can solve this integral and get me an answer in that form that has an n in it. Okay, and that's the name of the game. That's how you do this problem once and not infinity times. Okay, and I'll make sure that when John rolls in on Wednesday, that's where you pick up. But if you want to sanity check your answer, you should be getting something that smells vaguely like 2 over n pi cosine nt plus a phase shift that will either be positive or negative pi over 2. And if you add together all those cosines, you're going to get yourself a sawtooth. But isn't that amazing that with only 2 harmonics, we already got a feel that we were on the right direction? Pretty neat. Yes?
So could you integrate that answer in terms of n, like an indefinite integral, so that you're summing up n, like n is 1, 2, like, you know.
It wouldn't be an integral, it would be a summation. Because
What
it's
is it, an integral, like basically derived from a summation?
yeah, but a summation is when you're adding together discrete elements. You're adding to n equal 1, n equals 2, n equals 3. An integral is like when there's n equals 1, 1.1, 1.11, 1.111, like you're infinitely close together. So it's an infinite sum. Yeah. Cool. I'll see you on Friday. But you'll see you on Wednesday.